Hi, this lesson is about functions. So first let's talk about what functional notation is. So this is read as y is equal to f of x. F is a function of x, where x is the input and y is the output. F of x is going to be a definition of how to evaluate y. So here's an example. If f of x equals negative 2x squared plus 3x minus 1, this is going to get evaluated at x equal to negative 1 and then at x equal to 2. So that means first plug in negative 1 everywhere there's an x. So that's what that should look like. And then you apply order of operations, PEMDAS. So here we need to do the exponent before we multiply. So negative 1 squared is 1, but then when you multiply it by negative 2, you'll get negative 2. And then 3 times negative 1 is minus 3, and then minus 1. And then we just have to combine these three, and they're all negative, so you're adding, and your result here is negative 6. So when x is negative 1, negative 6 is considered to be the value of y. And then we evaluate it at 2. So it's same steps we did before, except we're plugging in 2 instead of 1. So you end up with negative 3 as a result. Again, negative 3 would be the value of y when your x is 2. So if you wanted to use these values to graph them, the way we did in the previous lesson, one point on the graph of f of x would be negative 1, negative 6, and another point would be 2, negative 3. Okay, in the next example, f of x is a rational function. Remember, rational functions have at least one variable in the denominator, and in this case, I have a variable in the numerator and the denominator. We are going to evaluate it at x equal to negative 2 and at x equal to 0. So when x is negative 2, f of negative 2 is 3 times negative 2 over negative 2 plus 5. That leaves us with negative 6 over 3, and negative 6 divided by 3 gives me a value of negative 2. So again, if this was something I needed to graph, which we will in the future, one point on the graph will be negative 2, negative 2. When x is negative 2, your y is negative 2. And when you plug in 0, steps are similar. I have 3 times 0 over 0 plus 5. That leaves me with 0 over 5. So it is okay to have a 0 in the numerator. And so 0 divided by 5 gives me a value of 0. Remember, the reverse would not be okay. If that was what occurred, then your answer would be that it would be undefined. And when that's the case, then that value would simply not exist on the graph. Okay, so a function is going to be a rule that assigns to each element of x in a set exactly one element of f of x called y. So for the last few examples I did, I plugged in one value of x and I got one value back for y. And that's what will occur when you have a function. We usually call the independent variable x. Doesn't have to be, but that's your input value. Other variables could be used. X is the most common. And the output, the value of f of x, is usually called your y. So different types of functions are here. The first one is considered to be a linear function. This is actually in the slope-intercept form, mx plus b. The second one is called a quadratic function. The second degree there is what makes that quadratic. Um, the third example is another rational function. And the fourth example is what we would call a radical function. Okay. The following examples in green are not functions, meaning they would not follow the definition that I mentioned earlier, which is that for one value of x, you get one value of y back. So in these examples, that's not the case, because if I say y squared equals x, if you solve this for y, you'll get that y is equal to plus or minus the square root of x, which means for one value of x, I would get two values for y, the positive and the negative counterpart. So for example, if I said, all right, what if x is equal to 4? Then y would be plus or minus root 4, which means plus or minus 2. So when x is 4, y is 2, and when x is 4, y is also negative 2. That cannot occur. You can't have two different values of y for one value of x when you have a function. So although this is a definition between two variables, it is not considered to be a function. And the second example on the right is very similar. This is actually the equation of a circle with a center at 0, 0, and a radius of 4. But this one is also not a function. If you were to solve this for y, you would also get plus or minus the square root of 16 minus x squared, which means that for any value of x, I would get two different values um, of y, or it's possible to get two different values of y. So these next few examples will give you tables of values, relationships between x's and y set up in a table, and all we need to do is determine if they show the relationship of a function or not a function. When it's not a function, we're just going to call it a relation. So in the table on the left, my x's and y's are as follows. So when x is negative 2, y is 4. When x is negative 1, y is 1. When x is 0, y is 0. And when x is 2, y is 4. Based on the numbers that I see in this table, this is a function. For any single value of x, I get one result for y. But number 2 is not a function because when x is 1, y is negative 1. But when x is 1, y is also positive 1. And the same thing occurs here. When x is 4, y is negative 2, and when x is 4, y is also positive 2. So because I have more than one answer for y for one value of x, this would be considered not a function. It is called just a relation. Okay, you can also define functions from verbal definitions. So in other words, you'll given words and we're going to state it in mathematical notation using functional notation. So in the first one, it says to express the rule as a function of f of x, cube, then subtract 5. So x is my independent variable. So cube it, and then subtract 5. So my function would be x to the third minus 5. So that's a translation of those words. And in the next one, we have h of x, add 1, then square it. So that means we're going to add 1 to x, which is what's happening here. And again, x is your independent variable, and then square the whole thing. So h of x is x plus 1 to the second power. The x plus 1 is in parentheses, and that's the translation. So in this next example, it says the perimeter of a square is defined by the formula P is equal to 4 times S. So square has 4 equal sides. If you call each side S, the perimeter is the distance around that shape. So that's why it's 4 times S, because there's 4 of them. So S would be your input, that's your independent variable, and P would be the output, that is the dependent variable. And so the question is to define S as a function of P, which means solve this for S. And so that's pretty easy to solve. All you have to do is divide both sides by 4. So you get S is equal to P over 4. And when it's stated like this, you would consider P to be the independent variable, and S would be dependent on that because we have redefined it in a different way. Okay, so we have a definition here called the net change in the value of a function. And when you see the phrase net change, it's referring to a difference in two values. And so if we need the net change in a function, it means that we're going to be subtracting two values of f of x. So the net change from x sub 1 to x sub 2, as long as the x sub 1 is less than or equal to the x sub 2, then the net change will be f of x sub 2 minus f of x sub 1. In other words, subtract, put the bigger value of x in first minus the smaller value of x, and then subtract the y values. So here you're asked to find the net change for f of x equal to negative 2x squared for x from negative 1 to 3. So the net change will be, by this definition, will be f of 3 minus f of negative 1. So I just have to plug in the 3 in here, minus, and then I plug in the negative 1 in here. So I get negative 2 times 27 minus negative 2 times negative 1. That becomes negative 54. Here there's 3 negatives, so it's still a minus. So it's negative 54 minus 2, which gives me a net change of negative 56. Okay, here's another one. You're asked to find the net change of g of t equal to 3 over t squared for t from 2 to 4. So I'm going to plug in g of 4 minus g of 2. When you plug in the 4, you get 3 over 4 squared. When you plug in the 2, you get 3 over 2 squared. That's 3/16 minus 3/4. You need a common denominator to subtract these two fractions. And so the LCD is 16. Therefore, the second fraction has to get multiplied by 4 over 4. That gives me 3/16 minus 12/16 for a final answer of negative 9 over 16. Okay, so now we're going to talk about the domain and range of a function. So the domain of a function is the set of all possible values of the independent variable, which again, we often call x. It doesn't have to be. Like in this example, my independent variable was t. So I'd be looking for the domain for t. But usually we call it x, and so independent variables, all possible values would be the domain of a function. And the range is the set of all possible values of the dependent variable, and that's what we usually call y. So when determining the domain and range, assume that only real numbers are acceptable. You can only plug in real numbers in for x, and your output, your y values, can only be real numbers. So in other words, no imaginary numbers, nothing that results in a number that is undefined. So we will have some restrictions for some functions. There may be some restrictions or numbers that need to be omitted. And so keep in mind that you can't divide by 0. So anything that results in division by 0 would have to be restricted from the domain. And imaginary numbers are not part of the real number system. So that would have to be omitted from the domain. And the range, right? No imaginary results. So the domain of all polynomial functions, now this is a very specific type of function, polynomials, is always going to be all real numbers. So linear functions and quadratic functions fall under that umbrella of polynomial functions. But there are more. Basically, a polynomial function will be any function where the exponent is a whole number, and you don't have any radicals, and you don't have any variables in the denominator. So here are several examples. This is a linear function, that's a polynomial function. This is quadratic, that's polynomial. This is considered to be a third degree polynomial because the highest exponent is 3. And this one here is a fourth degree polynomial because the highest exponent is 4. All of these have a domain of all real numbers. There are no restrictions to what x can be. X can be 0, x could be negative, x could be positive, could be a fraction or a decimal. Any value you plug in for x, you'll be able to find a corresponding value for y. So those are the easy ones to figure out the domain because it's always going to be all real numbers, but not everything is a polynomial function. And so examples of non-polynomial functions would be the first one, which is considered to be a radical. Remember, that doesn't fall in the definition for polynomials because 2 root x is the same as 2x to the 1/2. You can only have whole numbers in your exponent when you're talking about polynomials. The second one, that's considered to be a rational function because of this part. I have a variable in the denominator, so it's not a polynomial. And the third one is what we call also a rational function because I have variables in the denominator. So when you have a non-polynomial function, it is possible that you have some restrictions to the domain. So you can't assume that the domain here is all real numbers. And again, the domain means what are all the possible values that x can be. So here's some vocabulary regarding polynomials. The language that we use in math is just as important as the math. We all have to speak the same language and understand what the terms mean. So the example I gave is a fifth degree polynomial. The first 1, 2, 3 terms are called variable terms because they have variables in it. And the last one is just called a constant because it doesn't have a variable attached to it. So the first 3 terms are variable terms, and the one that determines the degree is the highest degree, and the number in front of it is called the leading coefficient. So -3 is the leading coefficient, and 5 is the degree of this polynomial. And again, because this is a polynomial, if you were asked for what the domain is, the domain would be all real numbers. Um, Here's a bubble representation of how you could show domain and range. So it's a more visual way of explaining it. And so on the left side, I have the domain, which is inside of this bubble, -3, 0, and 3. And on the right side, I have the range, which is -3, 0, and 3. The arrows between them indicate for every value of x what the value of y is. So you can see here that when x is -3, my y is 0 because it's pointing to the 0. So that's one point here. When x is 0, my y is -3. But there's 2 arrows coming out of 0. So when x is 0, y is also 3. And when x is 3, y is 0. This is not um, this is not a function because of this relationship and this relationship. I have 2 different y's for one single x. So when x is 0, y is +3 and -3. So you can pick out whether a relationship between x's and y's reflect a function by looking at a bubble diagram like this. But this next one is definitely a function. This one's very clear. When x is -1, y is 1. When x is 0, y is 1. When x is 1, when x is -1, y is -1. When x is 0, y is 1. When x is 1, y is 3. And when x is 2, y is 5. So for every value of x, there is a only one value for y. So this satisfies the definition of a function. And so we would consider my set here, the domain, to be the set of the numbers in the first bubble, and my range would be the set of numbers in the second bubble. This one is also a function. When x is -1, y is -3. When x is 0, y is also -3. -4. When x is 1, y is -3. And when x is 2, y is 0. So for every x, there's only one y. It is okay for the y's to be repeated. Like this is okay to happen. For every value of x, I only have one y. It's okay if the y's get repeated. You just can't have more than one x going to two different y's. Okay. So now we're moving on to identifying the domain of a rational function. And with rational functions, you will sometimes have restrictions because we have to avoid division by zero. Division by zero is undefined. So if that occurs, we have to avoid that. We have to say that's not part of the domain. It can't be an input value that you plug in. So state the domain in interval notation for the following functions. So this is the same notation that was discussed in a previous lesson for inequalities. We're going to be using that again. So we have f of x is equal to 5 over x plus 3. This is a rational function, and you want to figure out where is that denominator equal to 0. So I set that equal to 0, and I get x is -3. This is not a solution. This is a restriction. This is what we want to omit from the domain. So the domain is all real numbers except for -3. The way you show that with intervals is you would say that the domain is from -infinity to -3, union from -3 to infinity. And that means all numbers are in the domain except for -3. That's why we have parentheses around the -3. And just as a reminder, this is what it would look like with set builder notation. The set of all x such that x is not equal to -3. Okay, number 2 in green, g of t is equal to 7t over t squared minus 9. So this time my t is my independent variable, g of t is the dependent variable. Again, take that denominator, set it equal to 0. And I used the square root method, so I added 9 and took the square root of both sides. That means I have two restrictions to the domain here, at -3 and at +3. So I wanted to show you on a number line what that would look like. Everything I shaded is in the domain, except for -3 and 3. So I have like open circles in like dark blue at -3 and 3, which means I end up with 3 intervals, right? The interval from here to here, and then in the middle is interval 2, and then from here to here. So when I state my domain, you need 3 separate sets connected with this union symbol. So it's from -infinity to -3, union from -3 to 3, union from 3 to infinity. It's really common for students to forget this one in the middle. So perhaps like drawing the number line will help you remember. G of x is equal to x plus 2 over x squared minus 2x minus 48. Same as the first two examples, take the denominator, set it equal to 0. This one is factorable. And so you need to find two numbers that multiply together to give you -48. But when you add them, you get -2. And so what works is x minus 8 and x plus 6. So I get two solutions. 8 and -6, but they're not actual solutions, they're restrictions to the domain. So again, if you need the visual, you draw -6 and 8 on a number line, put open circles above them because they're not in the domain, and everything else that I shaded is in the domain. So again, I have 1, 2, 3 intervals that I need to show, and those intervals are shown right here. From -infinity to -6, union from -6 to 8, union from 8 to infinity. Okay, so now we're on number 4. And number 4 says h of u is equal to u squared over u squared plus 3. This time u is my independent variable. And h of u is dependent on that. So take the denominator, set it equal to 0. I again use the square root method, but this time I'm taking the square root of a negative number. Square root of a negative number is an imaginary number. So that means that there is no real number solution here, meaning that there is no value of u that would result in division by 0. No real number that if you plug it in here, you'll end up with a 0 in the denominator. And what that means is there are no restrictions on the domain. So although this is a rational function, this is a rational function with a domain of all real numbers. Right? In all the other examples, I got real numbers as a solution, which is why they were omitted from the domain. But in example 4, the solution to the denominator equal to 0 was imaginary, which means there are no numbers that need to be restricted from that domain. All right, so now we're going to talk about the domain of a square root function. With square root functions, you do need to be careful because there could be some restrictions because you want to avoid imaginary numbers. Again, if you have a negative inside of a square root, the way this one worked out, you're going to end up with an imaginary result. And when that occurs, you have to omit the values of x that would result in that. So, just as a reminder, the square root of negative 4 is 2i, but the square root of negative 7 is I root 7 because the 7 is not a perfect square. Okay, so here we want to state the domain, and this time we'll use set builder notation. F of x is equal to the square root of x minus 3. Just like we did with rational functions, you want to take the inside part of this and set it equal to 0. And when I do, I get x equals 3. Okay, so again, that's not a solution. That's just going to help us figure out what we need. So you want to put 3 on a number line. I'm colored in where the 3 is because 3 is in the domain. When it's equal to 0, like 3 minus 3, square root of 0 is just 0. So you do get a real number result when x is 3, so that is part of the domain. And then you have to check a test point to the left and to the right of 3 and figure out if the inside part will be positive or negative. If I plug in 2, that's going to be the square root of negative 1, which is I. So that cannot be in the domain. So that's why I said it's negative, no good. If I plug in 4, I'll get the square root of 1, which is 1. That is a real number. So your domain is all real numbers from 3 to infinity, including the 3. So with set builder notation, which is what you were asked to present, your domain would be the set of all x such that x is greater than or equal to 3. And just as a reminder, with interval notation, you would use a bracket to include the 3. So it would be bracket 3 comma infinity. Number 2 is a little bit more complex. It's h of t is the square root of t squared minus 4. Again, take the inside part, set it equal to 0. I use the square root method again, and I get 2 real numbers, negative 2 and positive 2. Again, now you have to test. So I put negative 2 and positive 2 on a number line. I put solid points above these two because these are in the domain. And then you check. If I plug in negative 3 in here, you'll end up with the square root of 5. That's a real number. If I plug in 0, you'll get square root of negative 4. That's imaginary. That's 2i. And if I plug in 3, you'll get square root 5 again. That's a real number. So where your result is positive, you get a real number result. So that's what I shaded. And where your result is negative, you get an imaginary result. So that's wasn't shaded. And so my domain is in two pieces, um, from negative infinity to -2 and from 2 to infinity. So again, that's how it would look as an interval with brackets around the -2 and the 2. And with set builder notation, it would be the set of t such that t is less than or equal to -2, or t is greater than or equal to +2. Okay. Um, in these next couple of examples, I'm giving you a picture, and we're going to state what the domain and the range is. Up until this point, we haven't really been talking too much about range. So when you have a graph, you just have to read the x-axis for the domain, the y-axis for the range, and you always want to state it from smallest to largest when you're talking about interval notation. So for the x-axis, you have to read from left to right, and for the y-axis, you need to read from bottom to top, because that's smaller numbers are to the left on the x-axis, bigger numbers are on the right. With the y-axis, smaller numbers are on the bottom, bigger numbers are as you move up. So in this one, if I'm reading my x-axis from left to right, the first value of x that I encounter is at 0. And then all these values here would be values greater than 0. So my domain is from 0 to infinity, including 0, because I have a solid point on the origin. When I read the range, you have to read the numbers from bottom to top. Now it appears that this is going to keep going down, right? Forever and ever, kind of slowly, but it keeps going down. So when I read this from bottom to top, this goes from negative infinity all the way up to that number, which is, again, y is 0. So your range is from negative infinity to 0, with, again, a bracket around the 0 because the point at the origin is solid. For number 2, looks like the picture of a parabola. My domain appears to be all real numbers, because this is going to keep going up, up, up forever, and it keeps getting wider and wider and wider. So it takes on every number all throughout for x. But your range, when you read from bottom to top, the first value in the range is this one right here at -3, and then it increases from there on both sides. Your y's just keep getting bigger from that point forward. So it's getting bigger on this side and this side, and looks like they're going towards infinity. So my range is from -3 to infinity with a bracket around the -3, because you have a solid point here at 0, -3. Okay. In the next example, it looks like I have this curve and like this purpley pink color, and everything is connected, but it looks like I have an open circle here at the point 1, 2. That means it's not defined there. Open means it is not part of the domain, it is not part of the range. So if this is the point 1, 2, then that means that my domain is all real numbers except for 1, the x value, which is the number 1. So it goes from negative infinity, so this means negative infinity, all the way up to 1, and then from 1 to infinity. So that would be your domain. And your range is similar, except I have to exclude the value of y at that open circle, and the value of y is 2. So my range is from negative infinity all the way up to 2, and then from 2 to infinity. Okay, so now we're going to talk about piecewise function. A piecewise function is a function that is defined by different rules depending on different values of the domain. So instead of just having f of x equals some statement, you're going to have f of x equals 2 or more statements. So in the first example here in blue, I have f of x is equal to x plus 2 when x is less than 0, and it's equal to negative 2x when x is greater than 0. This is one function defined two different ways depending on what the values of x are. So the top part, the x plus 2 is a line. So even though it says less than 0, you want to start at 0 and then pick another number less than 0 and plug it into your statement of x plus 2. So I have 2 points to plot, 0, 2, and negative 1, positive 1. At 0, 2, I'm going to put an open circle because it didn't say greater, less than, or equal to. If it had said less than or equal to, I would be coloring in that point right there, right? But since it just says less than, I need to put an open circle at 0, 2, and then negative 1, 1 is this one right here. Connect that open circle to that one and draw going to the left, and there's your line, the x plus 2, the top part. Negative 2x, the bottom half of this, is also a line, but I'm only interested in values of x greater than 0. Again, start at 0. And then pick one number bigger than 0. So I plugged in 0 and you get 0. 1, you get negative 2. Again, because it's just greater than, this point is open. If it was greater than or equal to, I would have to color in the point at 0, 0. But it's just greater than. So I have an open circle at the origin, and then my other point is 1, negative 2. That's this one. Connect the open circle in that point going to the right and down, and there's the second half of that piecewise function. So they both get graphed on the same xy plane because this is one function defined two different ways depending on the values of x. So what's the domain of this? The domain, you can either read the graph or you can look at it right here. The top half is all negative numbers, and the bottom half are all positive numbers. So the only number that's omitted is 0. So it goes from negative infinity to 0, and then again from 0 to infinity. But when I read the range, you really do need a picture. You need a graph. So both sides are going towards negative infinity, and then they're increasing from there all the way till they get to that value. There's nothing above 2. But 2 has an open circle, so my range is from negative infinity to 2, with a parenthesis around the 2, not a bracket. Okay, here's another piecewise function. I have h of x is equal to x squared for values of x less than or equal to 0, and h of x is equal to x minus 3 for values of x greater than or equal to 1. The top part is a parabola. But I'm only interested in graphing part of the parabola, only for values of x less than or equal to 0. So plug in a 0, and then plug in one number less than 0, like negative 1 or negative 2. Pick any number less than 0. So those 2 points are plotted right here. And so this is half of that U shape that we're used to seeing. And then x minus 3, I want to start at 1 and then pick something greater than 1. So I picked 1 and 3. So I get 1, negative 2, and 3, 0. And so those two are plotted right here. And that's a linear function, so you connect them going towards the right. Notice that this point is colored in and this point is colored in. That's because they're both have an or equal to part in it, right? So the top one is less than or equal to 0, and the second one is x is greater than or equal to 1. So when it's equal, that's when you want to color in the first point. So when I'm figuring out domain and range, you can either look at the graph or look at the function for domain. I find it easier to look right here. The top part is 0 and all negative numbers. The bottom part is 1 and all positive numbers. So the only numbers that are missing in domain are the numbers between 0 and 1. So the way you show that is like this. It's from negative infinity to 0 with a bracket around the 0, and then from 1 to infinity with a bracket around the 1. But when you're doing range, you need a picture. You're not going to be able to figure that out just from here. So when I read my graph from bottom to top, the first value of y is this one right here, and that's -2. And then your y values will increase forever and ever. This side is also increasing forever and ever. So my range is from -2 to infinity with a bracket around the -2. Okay. So last topic in this section is on the difference quotient. The difference quotient is a definition. This is something you're going to want to memorize. For people that need to take calculus, this difference quotient will be very important near the beginning of the first calculus course. So we're basically just using functional notation and plugging it into that definition. So we want to evaluate the difference quotient for f of x equal to -3x squared plus 5. So first, let's do this part, f of x plus h. That means everywhere there's an x, which is here, you want to replace it with x plus h. So this is what f of x plus h looks like in this example. -3 times x plus h to the second power plus 5. Then the second part of the definition says minus f of x. So that's this piece. You're going to want to put that in parentheses because this minus belongs to both terms in that function. All over h. So regardless of what your function is, divided by h is always part of that definition. So that's just plugging in to the rule. Now the rest of it is just doing some algebra. So I need to square this. And that's what I did here. When you square or FOIL it out, you get x squared plus 2xh plus h squared. And then on the next line, everything else on line 2 just got copied down. On the next line, I've distributed the -3, and I have distributed this negative. So you get -3x squared minus 6xh minus 3h squared plus 5 plus 3x squared minus 5 all over h. Now there are some like terms on that third step. So this -3x squared cancels with a positive 1, and the positive 5 cancels with the -5. So I'm just left with -6xh minus 3h squared over h. That's a rational function on that line that I just wrote, that I pointed to. And rational functions always have to be left in, or it's a rational expression. Rational expressions always have to be left in simplest form. And so what I did was I factored out an h from here because I know that if I do that, I can cancel with the h in the denominator. So I get h times -6x minus 3h. Then the h that got factored out cancels with the denominator, and the difference quotient is -6x minus 3. So you're just evaluating the difference quotient. You're not trying to solve any kind of equation. You're just plugging into the difference quotient definition and simplifying it as much as possible. Okay, here's another one. This one's a little bit harder because your original function is a rational function, and you have x's in two places. So instead of using f of x notation, I'm going to express the difference quotient in terms of g of x, which would look like this. G of x plus h minus g of x all over h. So this is the g of x plus h part. Everywhere there's an x in the original function, you replace it with x plus h. And then minus g of x, well, that's what that looks like, all over h. Okay, so now I've created an expression that needs some manipulation because these two do not have a common denominator. In order to simplify and combine them, you need an LCD. The LCD is the product of the two denominators, x plus h minus 3 times x minus 3. So what that means is that I need to multiply the first one by x minus 3, the second one by x plus h minus 3 on the top and on the bottom so that I have a common denominator. So when you put that together, I distributed the 2 here, so I get 2x plus 2h times x minus 3 over the common denominator minus 2x times x plus h minus 3 over the common denominator. And this divided by h here that I have, I wrote it like this. Saves a little bit of space, and it helps me to explain what I'm going to do on the next line. So from here to there, I FOILed this out. So I get 2x squared minus 6x plus 2xh minus 6x minus 6h. And I distributed negative 2x across here. So I get minus 2x squared minus 2xh plus 6x all over the common denominator. And then I changed division to multiplication and took the reciprocal. So that's the way you handle fractions and division. Keep the first expression, which is this one, change division to multiplication, and flip the second expression. So divided by h becomes times 1 over h. Okay, so the numerator of the rational expression has some like terms that cancel. So these 2x squareds cancel, the 6x's cancel, the 2xh's cancel. So I'm really just left with negative 6h over x plus h minus 3 times x minus 3 times 1 over h. But now that h cancels with that h. And so my difference quotient is negative 6 over x plus h plus 3 times x minus 3. Okay, so this requires practice. Memorize the definition of the difference quotient and practice. Make sure you understand what functional notation is all about. And so here's one for you to try. The difference quotient is given, and you're asked to find the difference quotient for this linear function, negative 2x plus 5. So that's it for this lesson. Good luck.